Welcome back to Logic, Language and Information 2, and to this, the fourth in a series of lessons on mathematics and logic. Beginning with the basic definition, any infinitely long list of real numbers is called a sequence. We denote sequences by expressions such as a sub n in parentheses, indexed by numbers n in the natural numbers. The index n identifies the position of the term a sub n in the sequence. We've already seen finite sequences in the course of developing the semantics of predicate logic. For a k-place predicate, we use lengths k sequences of objects, or k tuples of objects, to describe the meaning of the predicate. In contrast, an infinite sequence is a list that keeps on going and going and going forever, where the entries, a sub n, are generated according to some rule. The most famous sequence is the Fibonacci sequence. Start with a sub 0 is 1 and a sub 1 is 1, and then continue according to the recursive rule that a sub n plus 2 is equal to the sum of a sub n plus 1 and a sub n. So we start up a sub 2 is 2, 1 plus 1 is 2, a sub 3 is 3, a sub 4 is 5, a sub 5 is 8, a sub 6 is 13, and so on. The natural world exhibits Fibonacci numbers in multiple ways, such as the number of petals on a flower, the number of the growth patterns of branches from the main stem of a plant, the patterns of scales in a pine cone. As a mathematical sequence, its entries keep on getting larger and larger without bound. It goes to infinity. In contrast, some sequences of real numbers get closer and closer to a fixed number. They converge to a limit. One of the first examples we all usually see of an infinite repeating decimal number, 0.999 repeated. Now, the sequence is generated by the rule a sub n is the fraction 10 to the power n minus 1 over 10 to the power n. So we end up with 0, 0.9, 0.99, 0.999, 0.9999, and so on. For this sequence, it is clear that it is heading towards a limit of 0.9 infinitely repeated, which we can indicate using an overline on the 9, like this. Now, if we apply the property labelled Roman 3 of the distance is less than predicate from lesson 5.3, which expresses that if the distance is less than every positive number, exactly when the two numbers are identical, so then we can conclude that 0.9 infinitely repeated is in fact identical to the number 1, because there is no positive distance epsilon between them. So back in a previous lesson, 5.1, we were introduced to the Archimedean approximation of pi. The version of the approximation sequence for inscribed or inside polygons illustrated here goes as follows. So we're actually working with a circle of radius 1 and diameter 2, so that pi comes out as equal to half the perimeter or circumference. At stage 0, we start with a 4-sided polygon, a square, each of whose sides are length the square root of 2. This comes from using Pythagoras' theorem for right-angle triangles. So p sub 0 is 1/2 of 4 times the square root of 2, which comes out as 2 root 2. Then we're proceeding at each successive stage by doubling the number of sides. So progressing to 8, 16, 32, 64 sides and so on. And using geometry, particularly Pythagoras' theorem, to calculate the length of the sides of the stage n polygon recursively. Now, we can evaluate the side length L sub n plus 1 as equal to the square root of 2 minus the square root of 4 minus L sub n all squared. This approximation is accurate to 2 decimal places by stage n equals 3, when the polygon has 32 sides. This is one more stage than is illustrated in the image, but try to draw it and it gets too close to a circle and you can't just differentiate. Okay, another quite differently behaved sequence comes from different formulas for a sub n depending upon whether n is an even natural number or n is an odd natural number. So, for example, suppose a sub n is 1 over n plus 1 if n is even, and so that's n is 0, 2, 4, 6 and so on. And suppose that a sub n is minus 1 over n plus 1 if n is odd, so n is 1, 3, 5, 7 and so on. So we get the sequence shown in the table where the entries alternate between positive and negative, but are still getting closer and closer in distance to the value 0, whilst never quite getting there. Okay, one more example to lead you into an exercise. Consider the sequence starting with a sub 0 is 0 and a sub 1 is 1, and then continuing according to the recursive rule that says a sub n plus 2 is the average of the previous two entries, a sub n plus 1 and a sub n. So the average is just the midpoint calculated by taking 1/2 of their sum. The resulting sequence is a repeated average or moving average sequence. This sequence begins with 0, then 1, 0.5, 0.75, 0.625, 0.6875, 0.65625, 0.671875, and so on. As written, we've gone to the first 10 entries and we get up to 8 decimal places in these 10 steps. Now, this repeated averages recursive rule plus the values for a sub 0 and a sub 1 together constitute what's called a second order difference equation with initial conditions. From the general theory of difference equations, and you're taking this on faith, we are not doing mathematics as such here, but rather logic, this class of equation can be solved to give an explicit solution. The general nth term, a sub n, is equal to 2/3 of 1 minus 1 over 2 to the power n when n is even, and 2/3 of 1 plus 1 over 2 to the power n when n is odd. Now, just from this explicit solution formula, which of the following options seems correct? Now, at this point, don't stress, we will formally define convergence and limits of sequence as in the next lesson. This exercise is just to get you thinking about it. Okay, so how did you go? The correct answer is B. The entries are getting closer and closer in distance to the number 2/3, even though the entries alternate between being a little bit above and a little bit below this target number of 2/3. Recall the distance is less than predicate, expressing that numbers x and y are less than epsilon apart in distance. We're going to be using this three-place predicate D together with quantifiers to precisely define what we mean by an infinite sequence of real numbers converging to a limit R. The epsilon in the third place of the atomic formula D a sub n R epsilon will give a bound on the accuracy or error margin, expressing how close the term a sub n is to this target number R. We're going to need to consider smaller and smaller values of epsilon to capture the idea that we are getting closer and closer to the limit number. For example, we could take epsilon in progression as 1 over 10, 1 over 100, 1 over 1,000, 1 over 10,000, and so on, in the pattern 1 over 10 to the power k, as the natural number k goes to infinity. This brings us to the end of this lesson on sequences of real numbers, and in the next and final lesson in this series, we will arrive at our goal and rigorously define convergence and divergence of sequences of real numbers in predicate logic. So see you then.